This is the presentation of our paper Adversarial Completion of Automated Annotations for Traffic Scene Understanding at ADP3 workshop at CVPR 2021.
The first building block of our proposed approach generates dense segmentation maps for three classes: drivable area, dynamic obstacles, and static obstacles, as the most important information needed for an autonomous operation of a vehicle on public road. We solely use stereo camera RGB images and the depth extracted from them to gain knowledge about the vehicle's immediate surroundings. The automatic labels exhibit noisy annotations which result in obstacles and the drivable road be not entirely labeled as such. To improve the labels, we propose to use an adversarial approach directly on the annotations domain. The key idea is that in a GAN framework, the discriminator gets automatically labeled and manually labeled segmentation maps. This leads the generator, which operates on the automatically labeled data, as input to adapt them and mimic the semantic layout of target labels.
Training data is annotated in a self-supervised fashion solely by utilizing depth information from stereo image pairs and RGB information, and with the help of some heuristics integrated into different training data generators. Drivable road is obtained by creating a row-wise histogram of the disparity map, better known as the disparity map, and fitting a linear model to it under the assumption of a locally planar road surface. Similarly, static and dynamic obstacles can be automatically annotated by using a column-wise histogram of the disparity map, also known as U-disparity map. Obstacles can be interpreted as locally planar surfaces that are positioned vertically in 3D space. The separation into dynamic and static obstacles is done by using heuristics that allow to identify, for example, vehicles, pedestrians, and smaller thin obstacles close to the vehicle as dynamic obstacles. Pixels not labeled by any of the three training data generators, or that are claimed by more than one training data generator, are labeled unknown, as uncertainty for these pixels is very high. The results can be seen on the right side. While the results are not flawless, most of part of the scene is interpreted correctly. To improve labeling quality, an additional GAN-based refinement step is used, as described on the next slide.
Our adversarial setup consists of source and target datasets DS and DT with image label pairs XY. In adversarial training, we only utilize labels Y. Here, with YSI, we denote the annotations generated from disparity maps in the previous step, and YTJ are the target labels. Every element of YTJ and YSI is a class of ID of 0, 1, or 2, representing one of the classes: drivable area, dynamic object, or static objects, respectively. Our annotations completion technique resides on a widely adopted tandem of adversarial and cyclic consistency losses. They provide both solid adaptation results and stable training procedures robust against mode collapse. Our goal is to learn the mapping function which transforms YSI to YTJ. To approximate such a mapping function, we train a network which consists of two generators, GS and GT, and two discriminators, DS and DT. In order to train the aforementioned network, we define the objective function LT, and similarly, we define the LS, so that our final objective function L of GS, GT, DS, and DT looks as follows. We analyze our approach both qualitatively and quantitatively. Here one can see the results of the qualitative evaluation. From top to bottom, we can see examples of original images, ground truth annotations, generated and translated annotations. It makes evident that our approach not just smoothens the generated labels, but learns meaningful information about the traffic scene. This is especially prominent in the regions corresponding to sidewalks.
Here we can see some exemplary experimental results when training DRN26 network on data that has been automatically labeled as proposed before. We can observe a quite good segmentation performance. Drivable road surface, which is the green overlay, and dynamic obstacles, is red overlay, are accurately identified as such. Static objects, like buildings, are also correctly predicted, which can be seen in a bluish tint. However, sky is also labeled as static object. There are also some systematic fail cases that can be seen on the right side, especially trucks from the side with uniform surface and where dynamic objects like trains are not identified as dynamic but as static objects. Here we present the quantitative evaluation. At first we have a look on the labeling performance itself in Table 1. Cityscapes dataset is of flawless quality and can be regarded as 100% correct ground truth, resulting in a mean IOU of 100% for all classes. We are very satisfied that for drivable area, our self-supervised approach reaches a very high IOU of 97% and for static obstacles of 86%. Dynamic obstacles are the hardest class due to high visual variance and many small obstacles. This also has effects in labeling quality, resulting in 54% IOU. The mean IOU over all three classes is 79%, which is quite good, regarding that labels are generated automatically. Next, we would like to compare results when training a segmentation network on manual training data versus our automatically annotated training data. In Table 2, we can see the results. While the network does not entirely reach a performance as when trained on manually labeled data, we still achieve considerably good results without ever seeing a manually labeled image. Especially drivable area and static obstacles deliver a comparable performance, while dynamic objects are not as good, which is especially due to labeling quality for this class. Overall, mean IOU for our cheap and fast approach is 75% compared to 88% when training on manual data. From our point of view, both manual and automatic labeling have their pros and cons. Undoubted is the high quality and granularity of semantic classes with manually labeled data, resulting in good results when training networks on this data. However, the high quality literally comes at a price. Also, time requirements for densely labeling large datasets are an important factor that needs to be considered, especially for industrial and commercial applications. Portability can also be an issue when an already existing dataset should be used with another camera or for different environment, for example, a different country, or when usage of public datasets is prohibited to use in commercial applications. Our approach introduces noise in the labels and also cannot offer the same granularity in semantic classes, as the first labeling step is a non-learning method solely based on geometric and RGB information. As a consequence, while the obtained results when training a segmentation network on this automatic data are quite good, they do not entirely match the results of a network trained on perfect manual training data. However, the cost for labeling is extremely low, and annotation is fast with roughly 2 seconds per image, especially when comparing to 5,400 seconds as reported from the authors of Cityscapes dataset per frame. This allows our approach to scale well with a huge amount of required data for making autonomous driving road vehicles reality. This also affects the portability, which is easily accomplished by automatic annotation, as data for new cameras or new environments can be acquired without a huge effort. So in conclusion, manually labeled data is still the upper bound for semantic segmentation. However, we have an almost unlimited scaling for our disparity-based labeling approach. And also a subset of original labels suffices for improving automatically generated semantic maps. This makes our approach ideal for fast and cheap prototyping, for providing training data while manual data might not yet be available, and it can also partly substitute manually annotated data.